In this video, we are continuing our chemistry discussion. So for elements to become stable, as we talked about it in the previous video, we said that elements that do not have a filled electron shell, especially that last electron shell, if their last electron shell is not completely filled up with electrons, we consider those elements unstable. An unstable element is not able to stay on its own because it's highly unstable. It would have to bind to other elements to get the electrons that it needs for it to become stable. One way of doing that is elements, they go ahead and share their electrons together for them to become stable. And so when they share electrons together, we refer to that bond that's going to hold now those two elements together. We refer to it as a covalent bond. So as you can see right here, we have a carbon, and you can see that this carbon is bound to 4 hydrogens. This right here, this line is representing basically the bond that's holding this carbon to that to the hydrogen. And so this bond right here, we refer to it as a covalent bond. What's a covalent bond one more time? It's where the carbon is sharing its electrons with hydrogen and vice versa. And by sharing their electrons, each element is going to get the electrons that it needs, and therefore each element is going to become stable. So you can see right here, hydrogen on its own is unstable, and carbon on its own is unstable. But when they go ahead and they share their electrons together, collectively they will become stable. So let's go ahead and take a look at an example, and we're going to talk about how carbon is really sharing its electrons with hydrogen. So here are a few examples of the covalent bonds. So let's go ahead and take a look at it together. So if you have the periodic table in front of you, you would see that hydrogen has an atomic number of 1. So as we talked about it previously, the atomic number tells you how many electrons hydrogen is carrying. And so hydrogen, its atomic number is 1. So if I go ahead and draw the electron shells for hydrogen, I'm just going to draw 1 electron shell, and this 1 electron shell is carrying 1 electron. Electron, I'm going to note it with an E for electron and negative, just to kind of remind you that electrons carry negative charges. So hydrogen is actually unstable. Now, why is it unstable? The reason why it's unstable, it's because it's only carrying 1 electron shell, and that 1 electron shell is not filled up completely. We previously talked about how that first electron shell, for it to be completely filled up, it needs at least, or it needs a maximum of 2 electrons. And as you can see, hydrogen is only carrying 1. So how many more would hydrogen need for it to become stable? It would need 1 more electron so that it can have those 2, and that would fill up its electron shell. So therefore, hydrogen is going to have to find another element to get that electron that it needs. And so if you have, let's say, 2 hydrogens around, so let's just go ahead and draw the electron shell. So here is the hydrogen with its electron. I'm just going to note it with a circle right here in its electron shell. And let's say that there is another hydrogen with its electron right here. And so both of these hydrogens on their own, they are unstable because their electron shell is not completely filled up. So what they're going to do is that those 2 hydrogens, they're actually going to share their electrons together. And by sharing their electrons together, they're both going to become stable. And so this bond right here that I drew between the two hydrogens is the bond that's going to hold those two hydrogens together, and we call it a nonpolar covalent bond. Covalent because they are sharing their electrons. And again, sharing is not the same thing as giving it up. Like this hydrogen, so this hydrogen right here is not, so this hydrogen right here is not giving up its electron. It's not just totally giving it up to this hydrogen. Otherwise, I mean, if this hydrogen gives up its own electron, it's going to have 0 electrons. So what is it going to be? There is no element with 0 electrons, and so it's not giving up its electron, it's actually sharing its electron. So there's a huge difference between saying sharing and between saying I'm willing to give up my electron, because that's another bond that we're actually going to talk about when elements just give up their electrons. So here, hydrogen is just sharing its electron. So this hydrogen is willing to share its electron with this hydrogen right here. And so when they are sharing their electrons, they're both going to have, they're both going to get the electrons that they need. So this hydrogen right here now has 2 because it has its own, and this hydrogen is sharing its electron with it. And so they're both going to become stable because they are sharing their electrons together. And their electron shell is now going to be filled up with 2. Why do we call it nonpolar? Nonpolar means that those 2 hydrogens right there, they are sharing their electrons equally. So you don't have an element grabbing on more to the electron or trying to pull it more towards itself. That wouldn't be considered equal sharing. But in this case, they are equally sharing their electrons, and so we refer to it as nonpolar. Let's take a look at another example. So if we go ahead and take a look at carbon on the periodic table, you would notice that carbon has an atomic number of 6. That means that carbon has 6 electrons. So if I draw the electron shells for carbon, that first electron shell is going to carry a maximum of 2. And then I'm going to have to draw a second shell since I need to reach 6. And so I'm going to put 4. And so 2 plus 4 would give you 6. Let's take a look at the last electron shell for carbon. So the last electron shell for carbon only has 4 electrons. Now, is that completely filled? No. For that second shell to be completely filled, it needs 8 electrons. So as you can see, carbon only has 4, and that would mean carbon is unstable. Again, it's unstable because that last electron shell is not completely filled. So how many more electrons would carbon need for it to become stable? It needs 4 more to fill that last electron shell. So if, let's say, hydrogen is around, and we know already hydrogen carries 1 electron, so let's go ahead and draw, first of all, like my carbon, and I'm just going to put the 4 electrons that carbon is carrying in its last electron shell. So carbon would need 4 more for it to become stable. So let's say hydrogen is around, okay, and hydrogen is carrying 1. Now, hydrogen on its own is unstable, and carbon on its own is unstable. And so therefore, what they're going to do is they're going to, like, let's go ahead and help each other out so that we're both going to become stable. And so what they're going to do is this hydrogen is going to share its electron with carbon, and that would mean that this hydrogen right here is stable. Why is this hydrogen right here stable? Well, because this hydrogen right there, it got the electron that it needs. Remember, hydrogen just needs 2 electrons in its outer shell for it to become stable. And so now hydrogen is stable because carbon was willing to share one of its electrons with it. Okay, but let's take a look at carbon. Is carbon now stable? No, let's count together how many electrons now carbon has. So carbon has its 4 electrons, the original 4, and because hydrogen is now sharing one of its electron with carbon, carbon has now 5. Okay, 5 in its outer shell. That's still not full. You need 8 in the second shell to be completely full. And so therefore, carbon is still not stable. So if there is another hydrogen around, it's going to go ahead and share its electron with it. So now how many electrons does carbon have? It now has 6. Almost there, but it's still not filled. So carbon is going to find another hydrogen to share its electron with it. And so now carbon has 7 electrons. And then there has to be another hydrogen willing to share its electron with carbon. And so now carbon is stable. Why is carbon stable? Let's go ahead and check it out together. So carbon has its original 4 right there, and then 5 from this hydrogen, 6, 7, and 8. So now carbon is definitely stable because it got its electrons, like the 4 more electrons that it needed to fill up its last electron shell. So one more time, for elements to become stable, the last electron shell must be completely filled. For hydrogen, it just needs 2 electrons in its outer shell for it to become stable. For carbon and for so many other elements, their last electron shell needs to have 8 for it to become stable. And so does that mean all other elements need to have bonds between themselves and 4 other elements? No, it doesn't have to be with 4 other elements. It just depends how many, does each one need, and based on that, you would decide how many bonds you would have between the elements. And so right here, since carbon is sharing its electrons with hydrogen, when they share, we refer to it as a covalent bond. And because they are sharing it equally, we refer to them as a nonpolar covalent bonds. This is just another example down here talking about how oxygen is also unstable. So oxygen is unstable because, again, its last electron shell is not completely filled up. So it can go ahead and actually share its electrons with another oxygen for it to become stable. So oxygen has 6 in its last electron shell, so that would mean it needs 2 more. And so it can go ahead and share 2 electrons with another oxygen, and that would make it stable. So let's try this out together. So let's say that you have a nitrogen element, and you have a bunch of like hydrogen elements, and you want to figure out how would they bind together. So how many covalent bonds is going to form between a nitrogen and a hydrogen. So what you would want to do first of all is figure out how many electrons is nitrogen carrying. So nitrogen is carrying 7 electrons since its atomic number is 7. What you would want to do is go ahead and draw the shells. So the first shell is going to get 2, and then the last shell is going to get 5, right? So 2 plus 5 is 7. For hydrogen, we know that hydrogen is just going to be carrying 1 electron, okay? Take a look at each element. Is hydrogen stable? No, it's not, because it's only carrying one, and that would mean hydrogen needs another electron for it to become stable. Let's take a look at nitrogen on its own. Is nitrogen on its own stable? No, it's not stable because the last electron shell only has 5, and as I said, I need to reach 8 for it to become stable. And so therefore, since nitrogen has 5 in its last electron shell, how many more would you want to add to that last shell to become stable? So 5, I would need 3 more, right? 6, 7, 8 to fill it up. And so that would mean that nitrogen is actually going to bind with how many hydrogens? It would actually bind with 3 hydrogens for it to become stable. Why 3 hydrogens? Because since hydrogen is carrying 1, by sharing with 3 hydrogens, the nitrogen is going to get the 3 that it needs to reach 8 for its last electron shell. One common mistake is that if you think like nitrogen, as I said, has a total of 7. If you think of the entire total and think like, okay, nitrogen just needs 1 more to reach 8, that would be incorrect. You don't think of the total of how many electrons nitrogen has. You only think of how many does it have in its last shell. So the last shell only has 5. And that last shell, for it to be filled, it needs to have a total of 8. Only the last shell. So think of the last shell. So since it only has 5 in its last shell, to reach 8, you need 3 more. Not just 1 more, because I'm not thinking of, one more time, don't think of the total. And that's, again, a common mistake, is that students would just look at the total and they say, okay, it has 7 total. For it to reach 8, it just needs 1 more, and that would be incorrect. Don't think of the total. Think of how many electrons is in the last shell and how many more it would need to reach 8 and for it to fill up that last electron shell. So one way elements can be stable is for them to share their electrons, and we are going to refer to those bonds as covalent bonds. When the elements are sharing their electrons equally, we refer to it as a nonpolar covalent bond, and when they are not sharing it equally, we refer to it as a polar covalent bond. What's an example of a polar covalent bond? So for example, if we talk about H2O, which is water, water has 2 hydrogens and 1 oxygen bound together. Each one is unstable on its own, so oxygen is unstable on its own, hydrogen is unstable on its own. So when they go ahead and they share their electrons, the thing is, oxygen tries to pull the electrons more towards itself. And as we know, electrons are negatively charged. So when oxygen tries to pull the electrons more towards itself, it ends up with a slightly negative charge, and hydrogen ends up with a slightly positive charge because, again, the electrons are more pulled towards the oxygen. Because oxygen is pulling those electrons more towards itself, we say that oxygen is not really sharing those electrons equally with hydrogen because it's trying to pull it more towards itself. And that would be an example of a polar covalent bond. So polar covalent bond is when the elements are not sharing their electrons equally. A nonpolar covalent bond, kind of like the example we already talked about, the carbon bound to 4 hydrogens. The electrons there are being shared equally, and so carbon is not going to carry a negative or a positive charge, neither would the hydrogen, because they are sharing it equally, so that you're not going to see any charges. Versus with water, you will see that oxygen is going to carry a slightly negative charge and hydrogen is going to carry a slightly positive charge. And so that's the main difference between a nonpolar covalent bond and a polar covalent bond. Now, there is another way for elements to become stable, and that would be an ionic bond. An ionic bond is where electrons are either losing or gaining electrons. So the elements, they are not sharing their electrons. Um, they are actually giving up their electron. So one element would give up its electron and the other element will go ahead and accept that electron. And that's going to be known as an ionic bond. And an ionic bond, the reason why it's called ionic, because when elements give up their electrons or accept electrons, we refer to them as ions. And ions, because they are either losing an electron or gaining an electron, they will start carrying charges. If you remember, when you look at a periodic table, none of the elements on the periodic table are carrying any charges. And that's because they have equal amounts of electrons and equal amounts of protons. But if any of those elements lose one of their electrons or gain an extra electron, they are going to start carrying charges. And we start referring to those elements, we start giving them the term ions. So let's go ahead and kind of take a look at an example. Alrighty, let's take a look at an example of an ionic bond. So sodium, if you look at it on the periodic table, sodium has an atomic number of 11. And chlorine has an atomic number of 17. What does that mean? It means that sodium has 11 electrons and chlorine has 17 electrons. So for us to draw the electron shells for sodium, I would draw the first shell, and the first shell would only have 2. You can't put more than 2 in the first shell. And then you would draw a second shell, and that second shell is going to have 8. Again, you can't add more than 8 in the second shell. So 2 plus 8 is 10. So you have to draw a third shell, as you can see right here, and you would put 1 electron in that last shell. So 2 plus 8 plus 1 would give you the 11 that sodium is carrying. Now, is sodium on its own stable or is it unstable? How do we determine that? Look at the last electron shell. Is the last electron shell filled? No, it's not. It's only carrying 1. And for that last electron shell to be filled, it needs to have 8. And so since it only has 1 and not 8, sodium on its own is unstable. Let's take a look at chlorine. Chlorine has 17. So I would draw 2 in the first shell, 8 in the second shell. So that would give me 10. And then I would have to draw 7 in the last shell. Okay, let's take a look at the last electron shell for chlorine. Is it stable? No, it's not, because it's only carrying 7. And as we said, for that last electron shell to be completely filled, you need to have 8. So sodium and chlorine, when they are put together, what are they going to do? Sodium doesn't want to share its electrons with chlorine. What sodium wants to do is actually give up that last electron it's carrying in its last shell. Why? Because once sodium gives up that last electron it's carrying, it's going to have that second shell filled with 8. So sodium is willing to actually just give up its electron because once it does that, its second shell is going to be completely filled. Chlorine is actually willing to accept that electron because chlorine only needs 1 more. So this is what's going to happen. Sodium is going to completely give up its electron. And because sodium is willing to give up its electron, which is a negative charged electron, sodium is going to end up with a positive charge. Why is it now positively charged? Because it just lost 1 of its electron. Chlorine was very happy accepting that electron because that's all chlorine needed, an extra electron. So chlorine, after accepting an extra electron, it ends up with a negative charge. And so as you can see now, sodium is going to be called a sodium ion because now it's charged, and chlorine is now going to be called chloride ion because now it's carrying a charge. And if you notice, they are oppositely charged, and we always say opposites attract. So the positive charge and the negative charge, um, the two ions are now going to be attracted to one another. And that attraction, we refer to it as an ionic bond. So an ionic bond is a bond that's going to occur between a positive ion and a negative ion. And again, how did we usually, like, how do we get positive ions and negative ions? Is that this element right here lost one of its electrons, and that one right here gained an electron. Uh, Actually, elements could lose more than one electron, but the example right here, sodium just needed to lose one of its electrons to become stable. And let's take a look at it. Take a look at the last shell sodium has, and it is completely filled with 8 electrons. So sodium ion is stable. Take a look at the last electron shell for that chlorine ion. It has 8, and so therefore it is also stable. And so the bond, the ionic bond between a sodium ion and chlorine ion is basically going to result in sodium chloride, and sodium chloride is basically table salt. So the salt that you sprinkle on your food, etc., that salt is basically a sodium ion bound to a chlorine ion. So one more time, that's how, basically sodium chloride, which is salt, it's just a bunch of the sodium ions bound to a bunch of chloride ions. And again, that attraction that's going to happen between them is going to hold them together, and we refer to it as an ionic bond. There's a third type of bond called hydrogen bond, and a hydrogen bond is basically when you have a positive hydrogen ion bound to another negative ion. So we know, we kind of drew already water together. So water is an oxygen bound to 2 hydrogens, and remember how we said oxygen bound to 2 hydrogens, those are going to be covalent bonds, but they are polar covalent bonds because the oxygen, as you can see, the oxygen is kind of more greedy. It's trying to pull the electrons more towards itself. We refer to it as it has a high polarity, but oxygen is going to end up with a slightly negative charge, and hydrogen is going to end up with a slightly positive charge. So let's say this is one water molecule right here, and this is another water molecule. Can those 2 water molecules actually bind to one another? Yes, they're going to bind to one another via what we call a hydrogen bond. So the negative side of this water molecule is going to be attracted to the positive side of another water molecule. And so that attraction is, we call it a hydrogen bond because it's attracted to the positive hydrogen ion. And so therefore, we call it a hydrogen bond. So hydrogen bonds, you are going to have a bunch of hydrogen bonds between water molecules. So each water molecule is going to be attracted to other water molecules because one side of this water molecule is negatively charged, and one side of the other water molecule is slightly positively charged. And so you are going to have hydrogen bonds holding all of these water molecules together. So if you have a glass of water which contains tons of water molecules, the water molecules in that in that cup, they are actually bound to each other via hydrogen bonds. To summarize, we talked about covalent bonds, and that's when elements share their electrons. Ionic bonds is when you have one element losing an electron and the other element accepting that electron. And then hydrogen bond is the bond that's going to occur between a slightly positive hydrogen and a slightly negative atom. It could be oxygen, it could be any other element. As long as it's slightly negative, you are going to have a hydrogen bond between the hydrogen and, again, whichever negative atom you have. We've probably all seen it before. We've seen light insects able to walk on the surface of water. And the reason why they are actually able to walk on the surface of water, because as we said previously, water molecules, they're bound to each other by a bunch of hydrogen bonds. Those hydrogen bonds, they're actually pretty strong, that they create what's known as a surface tension. And light insects, they're actually able to walk on the surface of the water. And the reason why they're able to walk on the surface of the water, because those insects are very, very light, that they cannot break the hydrogen bonds between the water molecules. Why can't we humans walk on the surface of water? Well, because we're too heavy. Okay, if we attempt it, we're just gonna sink. And why? Because we're too heavy. We are going to break the hydrogen bonds right away between those water molecules. So one more time, if here is a lake, okay, and up at the top of the lake, you will have the surface tension. And the reason, again, why you have that surface tension up at the top is because the hydrogen bonds between the water molecules closer to the surface is actually way stronger, even stronger, compared to the bond, like the hydrogen bonding that's going to occur deep within the water. So the hydrogen bonds occurring between those water molecules up at the surface is very strong, and it creates that surface tension. As long as those bonds are not broken, the insects are able to walk on the surface of water. Let's say an insect is walking on the surface of water and it starts to rain, you're going to notice that those insects are actually going to take off running because when it rains, the rain is going to come down with a lot of force, hitting the lake, and therefore it's going to start breaking the bonds between the water molecules. And once those hydrogen bonds are broken, the insect, if it's still on the surface of the water, the insect is going to start sinking because the surface tension is going to start breaking down. There is something known as cohesion of water and adhesion of water. Cohesion of water is when water molecules are bound to each other. Adhesion is when water molecules are bound to other surfaces other than water. You've noticed it when you water your plants. Have you ever noticed how on the leaf you end up with water droplets, and how those water droplets, they're attached to the leaf? So when a water droplet is attached to other surfaces like a leaf, like even your arm, so like your skin, a table surface, etc., this is known as adhesion. Why is adhesion and cohesion pretty important? Because when you water a plant or when you water a tree, for example, the water goes down to the roots. Now, for this tree to be able to stay alive, the water has to actually make its way all the way to the top so it can reach all the branches and all the leaves, etc. It can't just stay down there within the roots. So what happens is the water down there within the roots, they're going to bind to one another via cohesion, and they're actually going to start sticking to the inside surfaces of the tree, and they're actually going to stick to the surface of of the tree, and they're actually going to pull themselves upwards until they reach the very top. And so that's actually that's kind of showing you the importance of cohesion and adhesion. Another thing to talk about is the pH scale. So pH actually stands for the power of hydrogen, and the reason why we call it the power of hydrogen, because if you have actually too many hydrogen ions, the solution is going to become acidic. If you don't have a whole lot of hydrogen ions, we refer to that solution as basic. So we usually have what's known as a pH scale, and the pH scale goes from 0 to 14. The closer you are to 0, the more that solution is acidic, and that means it has a whole lot of hydrogen ions. The closer you are to 14, that means that you have less hydrogen ions and you have more of what we call hydroxide ions. Hydroxide is an oxygen bound to a hydrogen. So if you have more hydrogen ions and less hydroxide ions, your solution is acidic. If you have more hydroxide ions and less hydrogen ions, then your solution is basic. What is neutral? So neutral is around 7, and neutral, that means that your hydrogen ions, so if we talk about neutral, neutral is basically your hydrogen ions are actually equal to your hydroxide ions. That means that you have the same amount. So when you have the same amount of hydrogen ions and hydroxide ions, it's actually neutral. It's not basic and it's not acidic. But if you have way more of those, so if you have a high amount of hydrogen ions, then your solution is acidic. If you have more hydroxide ions, then your solution is basic. Once they're equal, then it's neutral. What are examples of neutral solutions? For example, water, but not tap water, because tap water could actually be slightly acidic. Blood. Blood is a neutral solution. So your blood is, the pH of your blood is around 7.4, 7.5. It's actually pretty important for your blood to stay neutral. Lemonade, for example, soda, coffee, stomach acid, all of these solutions are pretty acidic. If you take a look at the example of acidic solutions that is listed out for you, coffee has a pH of 5 and stomach acid has a pH of 2. The closer you are to 0, the more acidic the solution is. And so therefore, your stomach acid is way more acidic compared to coffee. If you look at what are some examples of basic solutions, the cleaning products. So most of the cleaning products you have at home, they are actually basic. So baking soda, ammonia, bleach. You can see that bleach is way more basic compared to baking soda because it has a pH of 13. And so if you want to measure the pH of a solution, we usually have what we call pH strips. It's like a piece of paper, and but a special piece of paper, and you drop it in the solution, and based on the color change that you see, you can determine its pH, like where does it stand on the pH scale, and you can determine whether it's acidic, basic, or neutral. Now, as I said, our blood's pH is neutral, and it's extremely important that our blood's pH stays neutral. You never want your blood to become acidic, and you never want your blood to become basic. Why? Because if your blood becomes too acidic or too basic, that can actually lead to major problems. Like the person can start having seizures, or a person can can go into a coma, because again, their pH is not balanced anymore. Now, what do we have in our blood that can prevent that change of our pH scale? We have what's known as buffers. So the job of a buffer is to resist any pH change. Um, I just said that we drink a bunch of acidic solutions, like we drink coffee, we drink soda, lemonade. All of these are acidic solutions. So if I go ahead and drink like 2 cups of coffee, and then later in the day I drink a lemonade, and then later I drink a soda, does that mean my pH goes from a 7 to a 2? Is it going to start dropping because I'm drinking all of that acidic, I'm drinking all of these acidic drinks? And the answer is no, because we have what's known as buffers. And a buffer, its main job is to resist that change. How does it work? You can kind of think of it as like, think of the buffer. That's just an analogy. Think of it as a piggy bank. And so, and let's say that here is the gauge of your pH of your blood. And so we always, as I said, want to stay around 7. Let's say that your blood is starting to head towards the acidic side. Your buffers are going to quickly act to prevent that. And so as I said, an acidic solution is a solution that has way too many hydrogen ions. And so if your blood is starting to become acidic, that means that for whatever reason, you actually now have a bit more hydrogen ions in your blood. So what are your buffers going to do pretty quickly? They're actually going to absorb all of those excessive hydrogen ions you have. So they're basically going to be absorbing it out of your blood. So they're going to start absorbing all of those excessive hydrogen ions, returning your pH back to 7. And that's done pretty quickly. Let's say that, again, here is like the gauge of your blood's pH, and let's say that your blood is starting to shift towards the basic side. What's going to happen? Your buffers, so we said that a solution, if it's basic, that means you have less hydrogen ions. And so what are your buffers going to do? Your buffers, to actually help you out this time, they're not going to absorb the hydrogen ions. They're actually going to release hydrogen ions in your blood. So one more time, why are your buffers going to release hydrogen ions? Because if your blood is becoming basic, that means you have less hydrogen ions. And so to help you out, your buffers are actually going to release hydrogen ions in your blood, returning it back to 7. So the way buffers work is if the solution is becoming a bit acidic in your blood, the buffers are going to absorb hydrogen ions out of your blood. If your blood's pH is headed towards being basic, your buffers are going to release hydrogen ions in your blood. So buffers either absorb hydrogen ions or release hydrogen ions, depending on whether your blood is headed towards being more acidic or headed towards being more basic. And buffers do what they do to keep us, to keep your pH basically towards 7.